Sure. Okay, let's go ahead and actually pick up the example we were doing at the end of class on Monday, just so we can talk about how we draw like the face plan. Because I do think that's something that your instructor is interested in you being able to do. So we should practice it a few times. So I'll remind you what our situation was last time. We had, let me actually look at one thing here. Yeah, I was using x1 and x2. So we had that dx1 dt was equal to negative 2x1 plus x2, and dx2 dt was equal to 2x1 minus 3x2. We found all the things. I'll remind you what they were. We found the eigenvalues to be, let me continue with the labeling I used last time, just so it's not wildly different from what I wrote last time. Sorry, 1 second here. One. Yeah, cool. So we had lambda 1 equal to -4, lambda 2. Oh, sorry. Of them both lambda 1, that was no lambda 2 again. And lambda 2 equal to -1. And then the eigenvector with -4 was 1, -2. And the eigenvector with lambda 2 was 1, 1. And just as a point of interest, I'll ask again. I think the answer is still no, but has he talked about eigenlines in class? It's okay. Okay. So I'll say it again. The eigenline is just the line that contains the eigenvector. So this eigenvector goes over 1 and down 2. That means your slope is -2, right? Because it's your rise of -2 over your run of +1. So this is going to be the eigenline y equal to -2x. And this is going to be the eigenline y equal to x. So those are eigenlines. And then we also have the null clines, which you get by setting each of your differential equations equal to 0. So if we set this one equal to 0, and of course, yeah, okay, sure, fine. -2x1 plus x2 equal to 0. I'm going to try to isolate the x2, which is like my y thing. So this is going to be x2 equal to positive 2x1, or in other words, y equals 2x. And along that eigenline, sorry, null line, on that null line, all of our arrows will be purely vertical because there won't be any horizontal. The change in x1, which is our x, will be 0. So here we're thinking vertical direction lines because our dx1 dt is equal to 0. Similarly, for our second one here, we set 2x1 minus 3x2 equal to 0. And again, isolating the x2 thing, we get -3x2 equal to -2x1, or x2 equal to positive 2/3 x1. Or in other words, y equals 2/3 x. And along this one, they'll all be horizontal lines because the change in y is 0. And apologies, kind of, for going back and forth between x and y and x1 and x2, but it's a pretty common back and forth. It's kind of like how we go back and forth between y and f of x when we're talking about functions. Same idea here. We're thinking of x1 as the horizontal thing, x2 as the vertical thing, which we almost always think of the horizontal as x and the vertical as y. So it's a very natural back and forth. All right, so now we're going to try and draw the face plane. And oh, sorry, there was one more thing here. We had an initial condition, which was, where'd you go? Maybe we didn't, but there is one, which was x1 equal to 1 and x2 equal to 6. I suppose a better way of writing that would have been x1 of 0 equals 1 and x2 of 0 equals 6. So I said x1 equals 1, x2 equals 6 when t equals 0 is probably the easiest way to amend that. Okay, so let's go ahead and take a look here. We try and draw this thing. Come back to that in a minute. Three, 5, 6, 7, 8. Sure, it seems like enough. So what I don't want to do is I don't want to draw like a million direction arrows, right? Certainly there are tools that can do that for us. I've linked them in Canvas. I think your instructor also linked one in the most recent like week 6 page thing. If you look at his Canvas site. But what you want to do is kind of get an idea of how this thing looks. So we're going to draw the things and let's be, yeah, I've got 4 colors, sure. So we'll draw all the things. So first of all, the eigenlines. I've got y equals negative 2x. So that's going to be over 1 down 2. I forgot to bring my ruler again. I need to look for, I need to find that ruler. So I can just use a straight edge here. This always feels dicey though when you do it this way. Let's do that instead. Sure. All right, 1 sec. Here's my makeshift straight edge. It doesn't have to be perfect. Just trying to make it look decent. A reminder for these lines you draw, don't draw arrows pointing out of the ends because we might have arrows pointing actually inward. So there's my, what was this one here? This is my eigenline, which corresponded to the eigenvector of 1, negative 2, and the eigenvalue of negative 4. And let me double check here. Of course, I changed, but sorry, I accidentally changed the subscript there. That was my V1 and my lambda 1. Apologies. And then in black, we'll have our other eigenline, which is over 1 and up 1. Feels like it should be easier to draw, but we'll still be careful. So as you might have noticed, the process for drawing this face plane kind of seems like a pain in the butt. Which it is. It's a giant pain. No doubt about it. This one's your eigenvector V2 equal to 1, 1, corresponding to lambda 2 equal to negative 1. Reminder, when the eigenvalues are negative, that means you're being pointed towards inwards towards the origin, right? As time goes on and on and on, your x value and your y value are getting smaller and smaller and smaller. And what were the words I want to use here? There's a phrase I was looking for that I wasn't quite getting. And basically, like this is the line of strongest attraction or strongest repulsion, meaning you always travel directly in the direction of the eigenline. You never like veer from it. So all of your arrows either point directly in along the eigenlines if the eigenvalue is negative, or directly out if the eigenvalue is positive. Since both of these are negative, they're both going to point inwards. Yeah, let's also draw the null clines. So in green, we'll have the first null cline, which was y equal to 2x. And when I'm drawing a line, I'm really just, finding one point that isn't the origin and drawing a line. So I went over 1 and up 2. Draw my line here. I'm trying to make it look decent. We're always trying to make it look decent. Oh, finger got in the way. Okay, so along this line, which was my first null cline, where our dx1 dt is equal to 0, or if you want to think about it the other way, your dx dt is equal to 0, right? The change in x is 0. That means all of our arrows point vertically, right? There isn't any change in x. There's lots of change in y. So all of our arrows are going to point either upwards or downwards. Question. And actually, let me write my difference equations over again. So we have dx1 dt equal to negative 2x1 plus x2, and dx2 dt equal to 2x1 minus 3x2. Over here in quadrant 1, do we think these arrows are going to point upwards or downwards? Well, certainly the things closest to it, the eigenlines, they're both pointing, although they're pointing left or right, they're both pointing in a downward direction. So it's probably a good bet that these are also going to point downwards. But if you weren't sure, you could pick a point that was on the line. So if I pick, for example, the point 1, comma 2. So I plug in x1 equal to 1, x2 equal to 2. Well, we know that dx1 dt should equal 0, right? Because we're on the null line where dx1 dt is equal to 0. And that certainly will work. If I plug in 1 here and 2 here, I'll get negative 2 plus 2, which is 0. And for the y thing, or the dx2 thing, our dx2 dt will equal 2 minus 6, which is negative 4. Meaning, oh yeah, we're going to be pointing downwards. In fact, all these arrows on this part are going to point downwards. Because basically you can't change the direction you're pointing until you cross an equilibrium. And the only equilibrium here is the origin. So all those are going to point downwards, and all the ones down here on the other side of your equilibrium are going to point upwards. Exactly. And you can see that if you pick the point -1, -2, right? This part will still be 0 here, but this part now will be -2 plus 6, which is positive 4. So it's still pointing in a purely vertical direction, but now all of them are pointing upwards instead of pointing downwards. I will say, when both your eigenvalues are the same sign, when they're both negative, it's pretty easy to tell which way it's going to point, because it's always going to point in the direction it's either pointing towards the origin, if everything's pointing in towards the origin, or if both my eigenvalues were positive, they point in the direction that was away from the origin. It's like if this was the same sort of situation, but these eigenvalues were positive, these arrows up here in the first quadrant would point upwards, away, and these ones here would point downwards, away. So usually if they're the same sign, it's easy to tell. If they're opposite signs, it's a little more having to think about what's happening. Finally, for my last null line, which was the null line x2 equals 2/3 x1, or y equals 2/3 x, I'm going to go, well, let's see, my rise over my run is 2/3. So I'm going to go over 3 and up 2. Things are getting a little tight over here. So draw that one using my tried and true method of a piece of paper. I'm trying to make this look extra good. Ah, I think I failed. Oh, I really failed. I drew on the paper instead of. I'll tell you, need a real ruler. One more time. I think that works. Cool. So there's my other eigenline. x2 equal to 2/3 x1, if you prefer, y equals 2/3 x, which is giving us that dx2 dt is equal to 0. And I forgot for this green one up here, this is where x2 is equal to 2x1, or if you prefer, y is equal to 2x. I definitely do prefer using x and y versus x1 and x2, just because I think it's easier to think about graphing these lines in terms of y and x instead of having to make the quick translation from x2 to y and x1 to x. But it'll be like, and then finally, on this eigenline, that's not what it's called. This red one is not an eigenline, it's a null line. All of my arrows should be purely horizontal, because the derivative in the y direction is 0. So there's no vertical change, it's all horizontal change. So all these are pointing purely left, purely right. And based on what I said before, we can be pretty confident that the ones over here in the first quadrant should be pointing to the left, because they should be pointing in the direction that's going to get you closer to the origin. And then these ones down here in the third quadrant should be pointing to the right. Okay, so now, often what we do with something like this is say, okay, for this initial condition, for the initial condition that x1 of 0 is equal to 1 and x2 of 0 is equal to 6, draw the trajectory. So I'm going to go over 1 and up 6. So 1, 2, 3, 4, 5, 6. I'm starting like right here. And then the question is, which way do we get pushed? I always think about getting, like, which way. Push is the word I use here. You say, what direction do we go in? But I feel like we're getting pushed by the surrounding eigenlines and null lines. So I'm specifically between this blue thing and this green thing here. So I'm getting pushed down and to the left, to the right, sorry, down to the right. That's kind of it. I'm getting pushed down to the right. Now, if it's not easy to see that, and it takes some practice, I will admit. Like I wasn't always as good at this because I learned this relatively recently. What you can do is you can just plug in your initial conditions to your differential equations. So if I plug in 1 for x1 and 6 for x2, my dx1 dt at that point is going to be -2 plus 6, which is +4. And my dx2 dt is going to be, let's see, 2 minus 18, which is negative a lot. So I'm going over 4, I should say right 4 and down 16. Or in other words, I'm going down 4 times as much as I'm going right. So my vector should be pretty steeply pointing downward. So it's going to, well, not my vector, so the direction of travel at first. So I'm going to start going that way. But I know that when I cross my null line, I have to cross it in, well, for this green one, in this purely vertical direction. I have no choice, right? Null lines you always have to cross in the way things are situated. So we're essentially going to go this way. We're going to cross this purely vertically. And then now we're between these two things. We're going to get pushed down, but now we're going to push to the left, and we're going to come in towards the origin. As I said last time, the eigenlines are kind of like asymptotes. You get closer, you get asymptotically close to them either as you go in towards the equilibrium, which is the origin, or as you go away from the equilibrium, like out to infinity. That's what's happening. Yes.
Why one is vertical and one's horizontal?
Well, how are we finding the null lines?
It would equal 0.
Well, yeah, but what am I setting equal to 0? Specifically, to find the null lines, I'm setting this equal to 0 and this equal to 0, right? So when I set the derivative of x1 equal to 0, that means I'm saying that x1, everything is x, isn't changing. So there's no change in the x direction, which means everything has to be in the y direction. So that's why for this first null line in green, where dx1 dt is equal to 0, or if you prefer dx dt is equal to 0, there's no horizontal change, it's all vertical change. In the same way, for the red one, setting dx2 equal to 0 or dy dt equal to 0 means, oh, there's no change in the y direction. And maybe it'd be better if I labeled my axes here. This is x1 or x, this is x2 or y, right? For this red one here, there can't be any change in the y direction, so all the change is purely horizontal. Which is why we care about the null lines, because they tell us something that's kind of useful, helps us identify how this graph is looking. Yeah, good, very good question. I'm glad you asked. And then if you wanted to, you could kind of start with some other initial condition. And you're like, okay, well, how's this going to work? I would point out, and let me just again, but to kind of not make my graph look terrible, let's just pull up. Maybe. Where'd you go here? Sure. Is that it? I think that's it. Yeah, there we go. This is the one your teacher also referred you to. It's useful. There are better ones, but it's fine. But if we actually, graph this or plot it, so the change in x is -2 times x plus y, and the derivative of x2 or y is going to be 2 times x minus 3 times y. If you graph it there, and let's make it so we're going like to -10 and 10. You can change how big your screen's going to be. If we graph that there, that doesn't, so I will point out that does not look like what I graphed, right? So just looking at that, I must have done something wrong. I'll point out that looks a lot like a saddle. We're going in towards our equilibrium in one direction and out in the other direction. So let's go back and look at my equation. I probably did something wrong here. Yeah, I have a whole extra. What did I? Holy smokes. I think I forgot to delete part of what they already had there. So let's see. Now I have negative 2 times x plus y and 2 times x minus 3 times y. Okay, that should be correct. Much better. Right? Now everything is pointing inwards. So we can see, right, our eigenline here of y equals x. And what was the other eigenline? Y equals negative 2x, which is a little harder to see, but you can kind of see, oh yeah, look, y equals negative, along the line y equals negative 2x, you can kind of see that we're pointing straight in as well. And then if you pick an initial condition, like say 1 comma 6, approximately, you can see that, oh yeah, it has that kind of that same shape that we drew. But you can also start somewhere over here, or somewhere over here, somewhere over here. And notably, although again, I don't love this one personally because you can't actually draw the eigenlines or the null lines on there, which is unfortunate. But if you think about where our well, you can see the eigenlines. I meant the null lines there, either one really. Like one of our null lines is y equals 2x, right? So it's kind of like right there. And along that line, it's kind of hard to tell that all of your arrows are vertical. So yeah. So that's kind of the idea of graphing this is plotting typically these 4 lines, the 2 null lines and the 2 eigenlines, although again, he hasn't talked about eigenlines, so I don't know how much he's really gonna have you do that. And then kind of seeing what's happening. Let's look at another example here. Actually, one that I've kind of already printed out here. So here's another example, but I don't know how much I want. I think I kind of just more want to show you than work through this one. Sorry, I'm trying to keep things in order. I'm really not. There we go. There we go. Maybe you. No, you're something else. Okay, great. So here's another example of a thing. So come on in. So here is the phase plane already kind of drawn out for this system of differential equations. dx dt equals negative 3x plus 3y, dy dt equals 6x plus 4y. And really, the idea here isn't so much that we want to kind of find all the things, it's that we want to kind of look at the graph and be able to identify things. And yeah, I don't know how much I love this one actually when looking at it. You can kind of see along this line here in red, all of the arrows are pointing purely vertically. So that red line there would be our x null line, where dx dt is equal to 0. In a similar way, this purple line, where all the arrows are pointing horizontally, that's our y null line, where all the dy dt's are equal to 0. Which you can kind of see, right? If you set dx dt equal to 0, oh yeah, you're going to get negative 3x plus 3y equal to 0, which is going to give you y equal to x. So yeah, that's exactly y equal to x. Setting this one equal to 0 gives you something similar. I'm not super in love with this, so let's look at something else though. So let's take a look at this situation here. And again, I know this is unfortunately not an opportunity to really take notes because you can't really draw the whole thing and be like, I'm going to draw. So I want to point out that if you look at something like this, and here's your origin right here, you can kind of identify where the null lines and the eigenlines are. In my mind, it's almost always easier to identify the eigenlines. He says, while he looks at this, is like, what are the eigenlines? So the eigenlines are the ones that point either directly in or directly out. So it looks to me kind of like maybe, where was it there? I know I saw it before. Like I know I saw it when I was looking at it earlier today. I was like, oh yeah, it looks great. And now I'm like, I don't really see it at all. Sorry for my, let's see here. Look at my notes to myself here, which I've hidden from myself. There we go. Okay, yeah. So if you look in kind of this direction here, you can kind of see, oh yeah, those arrows all seem to be pointing in the inward direction. And if you continue on this way, right,
these arrows are, this line is kind of straddling arrows pointing up and to the left and up and to the right. So in between them, you can think, oh, well, they're pointing kind of perfectly in that direction there. Yeah, I don't know how, I'm like, kind of like, I feel like it's kind of a good idea, but also, So this is an eigenline. And then there's also one in the, yeah, some other terrible direction, like maybe I think it's like about this way. See, oh yeah, look, the arrows are pointing again, straight out, straight out. So let me ask you all a question. For this first eigenline I drew, my eigenvalue positive or negative? So if we're pointing inwards, which we are, that means the eigenvalue should be negative. So for this eigenline, our eigenvalue is definitely negative. For this other eigenline, our eigenvalue is definitely positive. I always found finding the eigenlines or identifying the eigenlines easier than trying to identify the null lines. So the null line is where you're looking for arrows that are perfectly horizontal or perfectly vertical. So let's see. Perfectly vertical. Like, where could it be? Let's take a look. Okay, yeah, I was hesitant, but yes. So typically when you're looking for perfectly vertical, you want to kind of look for the same kind of thing. If you can't see one that's perfectly vertical, you want to see kind of the difference between one that's slightly vertical and left and slightly vertical and right. So looking like right about here, I see one that's pointing up and slightly left and one that's up and slightly right. So between those two is probably where the perfectly vertical one is. And that seems to be true completely on this horizontal line. Right, all the arrows on that line would be totally pointing, well, here, down, 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 and over here, up, 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 up. So along this line, you'd have dx dt equal to 0, right? If your line is vertical, there's only change in y, there's no change in x. Can we find the horizontal one? Ugh, maybe. So I'm looking right here and seeing that this one actually looks pretty horizontal. So does this one. It looks like it's here, here, here. It kind of looks like it's along this line here. Point worth noting. In these cases where the systems are easy, like meaning there's no like, it's not non-linear. It's a very nice like dx dt equals a multiple of x plus a multiple of y. Dy dt equals a multiple of x plus a multiple of y. All your lines have to go through the origin. So if I'm starting like here, I'm trying to go through here, I'm like, cool, I can draw a line that goes to, right, like, I can make that happen pretty easily. So there we go, kind of like that. Is it perfect? No, but it's pretty close. So that's where my dy dt equal to 0 null line is. All right, so yeah, drawing these is always kind of the challenging part, which is why you should practice it on your. So I will say, oh, I forgot to give you the sentence form. Where's the sentence form? All right. Where was the thing I was looking for? Oh, I know what it was. In the most recent, like in section 10.1, he does assign a few problems where you're supposed to, where like you're given a system of differential equations and you're supposed to construct the faceplate, including the null lines. I would also encourage you to draw the eigenlines, but that does mean you have to do the work of finding the eigenvalues and the eigenvectors. Yeah. Yeah. So yes, the equilibrium, which is the origin. Well, let me actually write something down. So if we have what I consider like kind of the most basic situation, if we have a linear homogeneous system of differential equations, meaning it's the very, very basic system we've been dealing with this whole time, where your dx dt is just a multiple of x plus a multiple of y and dy dt is also just a multiple of x plus a multiple of y. If that's the case, then yes, well, certainly your eigenvectors have to, or your eigenlines have to go through the origin, and your null clients, if this is the case, have to go through the origin. Because essentially, if you're setting each of these equal to 0, if you set ax plus by equal to 0, you're just going to get the line by equal to negative ax, or y equal to negative a over b times x. And certainly the origin is one of the points you're going to get. You can set that down in front of you if you want. Same deal here. You're going to be getting y equal to negative c over d times x. So when your system is like this, where it's just your derivative of x, derivative of y as a vector is equal to the 2 by 2 matrix A, B, C, D times the solution vector xy, then yeah, everything goes to the origin. If he starts talking about non-linear systems of differential equations and or non-homogeneous systems of linear differential equations, we can talk about other things, but I don't want to trouble you with that if you don't have to learn about it. Some people cover it, some people don't. It kind of depends on who's teaching it. One way to think about, I'm not sure, actually, I forget what the description of what it means to be non-homogeneous is exactly. But typically, usually we think about a homogeneous thing is, well, homogeneous typically means that 0, 0 is our solution, is our equilibrium. Just to make sure everyone's on the same page here, if you had this system, dx dt equal to, let me make up something that's easy to solve, 2x plus y minus 3, and dy dt was equal to 4x minus 2y minus 2. This system is not homogeneous. The origin is not a solution, or I should say, it's not an equilibrium. Right? If you say each of these equal to 0, you're not going to get 0, 0 as a solution. I will point out that in this example, because I made it up to be easy, the equilibrium is the point x comma y equal to 1 comma 1. You plug in 1 for x and 1 for y, you're going to get 2 plus 1 minus 3, which is 0, and 4 minus 2 minus 2, which is 0. If you write the system as a matrix equation, it looks like dx dt, dy dt equal to the matrix, the coefficient matrix 2, 1, 4, negative 2 times xy plus the extra little piece here, the vector negative 3, negative 2. And that kind of extra piece there is what makes it not homogeneous. But again, I would say we won't focus on that too much unless we need to. All right, so I got papers everywhere. Let's go ahead and look at. Sure. I'm curious which way he's going to go next. Because we could either talk about how to classify things or imaginary things.
Imaginary.
Right at the very end, yeah. Yeah, sure. Let's go that way. Yeah, let's not go that way. So yeah. Let's talk about the thing that I think is easier to kind of comprehend for a minute here. So here's what I'll just say, blanket statement. The imaginary things are terrible. Not because like finding imaginary eigenvalues is hard, but solving a system with imaginary eigenvalues, the eigenvector part gets dicey. And so I probably need, and it's kind of ugly. Grant has actually some nice videos on it that I would encourage you to check out once we get there. I will also talk about it in class but I probably want more than 15 minutes to talk about it. And also, I have to make sure I remember how to do it right so that I don't screw it up, because it does, the math just gets a little bit weird. But let me actually, yeah, let's kind of talk about one thing in that vein. So leading up to these imaginary things. This pen is about to die, I think. Yeah, trash. Dead to me. Okay. Leading up to imaginary eigenvalues and vectors. And again, imaginary is probably not the best word to use. The better word is complex. So really we want to say complex. Meaning the eigenvalues will have a real part and an imaginary part, and the eigenvectors will have some real and imaginary parts as well. So a couple things to know. We define the square root of -1 to be equal to I, the imaginary unit. A few things we should know about this. I squared is equal to the square root of -1 squared, which is -1. I cubed is equal to I squared times I, which is -1 times I, which is -I. I to the fourth is equal to I squared times I squared, which is -1 times -1, which is +1. And then what I like to think of is you've kind of done a full cycle. It's kind of similar actually to the derivatives of sine. If you take the derivative of sine 4 times, you get back to where you started. If you raise I to a power 4 times, you get back to where you started. So I'll just point out that I to the fifth is I to the fourth times I, which is 1 times I, which is I. And then I to the sixth is going to be the same as I squared, which is -1. I to the seventh is going to be the same as I cubed, which is -I, and so on and so on. I to the eighth is +1. So every fourth power of I, you just get back the same thing you had before. So, right, I is equal to I to the fifth, is equal to I to the ninth, is equal to I to the 13th, and so on and so on and so on. And -1 is equal to I squared, is equal to I to the sixth, is equal to I to the 10th, and so on and so on and so on. And might as well finish off. -I is equal to I to the third, is equal to I to the seventh, is equal to I to the 11th. Every time you increase the power by 4, you're just multiplying by another I to the fourth. And I guess I might as well finish off, right? I to the fourth is 1, which is also I to the 8th, which is I to the 12th, which is I to the 16th, and so on. There is a good reason we care. Right? So most of the time, I'm not just saying stuff for the sake of saying it. Occasionally I am. But most of the time, I'm saying stuff because there's something useful we're going to see about it. And in this case, the useful thing, well, yeah, let me go that way. How about all my papers get everywhere? There's one thing I just want to make sure to say here. Where'd you go? What paper that I had? The problem with printing out all the things. There we go. Cool. Yeah. So you guys kind of remember maybe in 17A learning about Taylor polynomials for like a brief moment. Taylor polynomials, or like a linearization of something, and then there was also like a quadratic approximation of something. It's okay if you don't, but like you might. So let me tell you a couple things about Taylor polynomials, which are kind of really neat. So there's this whole branch of mathematics called Taylor polynomials, which basically is a way of using a polynomial to approximate a function. So you might have seen how back in the day, for example, if I wanted to find, I got time. If I wanted to find the linearization of, say, like f of x equal to e to the x at maybe the point where x was equal to 0, well, it's just the equation of the tangent line, right? That's what the linearization is, the equation of the tangent line. But the idea here is there's like a way of doing it with a Taylor polynomial, which just looks a little bit different. We're going to say, cool, f of x is going to be approximately f of 0 plus f prime of 0 times x minus a. This shouldn't be super surprising if you imagine it as f of x minus f of 0 equals f prime of 0. times, sorry, that's a 0, not an a, apologies. Times x minus 0, or if you want to think of it as y minus the y coordinate equals your slope times x minus the x coordinate. It's just the equation of a tangent line. But here's the bigger point. The bigger point is that you can extend this approximation to make it better. Like the linearization is cool, like for points near e to the x, but if you're thinking about drawing this, oh yeah, we can do this, cool, yeah, I got that. So if I draw e to the x, then here's my linearization or my linear approximation. It's the tangent line right there. Okay, but I can make my approximation, and we can find it, right? Or in this case, f of 0 would be 1, f prime of 0 would be e to the 0, which is also 1, and our linearization would be L of x equal to 1 plus 1 times x minus 0, which is just 1 plus x, which you could probably believe that's the equation of that line right there. But here's how we can make it better. We can make it better by saying I'm going to approximate f of x with f of 0 plus f prime of 0 times x minus 0 to the first plus f double prime of 0 divided by 2 factorial times x minus 0 squared. That's the quadratic approximation. I don't really actually care what it is, although I will say it is 1 plus. The nice thing about my derivatives here is the derivative of e to the x is always e to the x, and e to the 0 is always just 1. So it's going to be 1 plus 1 times x plus 1 divided by 2 times x squared. And the neat thing is that this parabola is a better approximation of e to the x. Let me show you because I can't really draw it very well. So if we take a look here, can I find it? Maybe. Desmos, are you still there? Nope, you're not there. You're here. Cool. All right. So I'm about to show you something that I think is really, really neat. Also, I'll try to find the link. There's you don't really know that much about Taylor polynomials, but there's just kind of a neat video from it's 3 blue, 1 brown, or 3 brown, 1 blue, whatever it's called. He has lots of cool math videos about lots of stuff. But if we look at this, if I graph y equal to e to the x, check this out. So here's my, well, actually, here's my 0th degree approximation. Not very good. But if I add on an x, okay, it's good near, and let's actually zoom in a little bit. If I add on the next term of my Taylor approximation, oh, looks even better for longer around the function. If I add on the next term, which is going to be x to the 3rd power divided by 3 factorial, even better for longer. And you can keep doing this forever. But the point is that this Taylor polynomial you can actually express e to the x as this Taylor polynomial. So you can say, cool, e to the x is actually legitimately equal to, not approximately equal to, actually equal to 1 plus, oh, sorry, no, yep, good call. 1 plus x squared divided by 2 factorial, which is just 2, plus x cubed divided by 3 factorial, plus x to the 4th divided by 4 factorial, and it just goes on and on and on forever and ever and ever. Okay, yes, we're going to get there. So there are 2 other really super duper important Taylor polynomials that we like, which we could derive what they are, but I'm just going to tell you what they are. So they're for sine and cosine. So the Taylor polynomial for sine of x and cosine of x centered at 0, which just means that's where you're doing the approximation at the beginning, are the following. Sine of x is going to be all the odd powers. It's x to the 1st over 1 minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and it just goes on and on and on. Cosine, being an even function, just like sine is an odd function, is all of the even powers. It's 1, which is x to the 0th, minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial. Here's the connection we're going to make that we will use probably eventually. Very likely eventually. At least when we talk about how the eigenvectors of the systems with imaginary or complex eigenvalues typically end up working out. This next fact that we're going to write down is actually where it's coming from. So this is actually, I think, a really, really neat thing. This is called Euler's formula, I think. Yeah, this is Euler's formula. Yes, it's pronounced Euler, not Euler. Okay, so here's what we're going to say. We're going to do e to the I times some angle. And we're just going to throw that into the Taylor polynomial formula. So reminder, I know, so let me actually just write it up here again. So just remember, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on and so on. I'm going to try and do this quick because I have 3 minutes. So here's what we're going to get. We're replacing every x with I times theta. So we're going to get 1 plus I times theta. I'm probably going to write out like 9 terms here. Plus I times theta squared over 2 factorial plus I times theta cubed over 3 factorial. I times theta to the 4th over 4 factorial. We go on and on and on. Let's go out to like the 8th power. It's usually way more terms than you would write when you're writing out. Okay, but now we're going to simplify this. So reminder, I to the first is I squared is -1, I cubed is -I, and I to the 4th is +1. And then it repeats. So check this out. This is going to be 1 plus I times theta. I squared is going to be -1, so this is going to be minus theta squared over 2 factorial. I cubed is -I, so minus I times theta cubed over 3 factorial. I to the 4th is 1, so we have theta to the 4th over 4 factorial. I to the 5th is I, so I times theta to the 5th over 5 factorial. I to the 6th is I squared, which is -1. So it's going to be -1 times theta to the 6th over 6 factorial. Whew. I to the 7th is -I times theta to the 7th over 7 factorial. And finally, I to the 8th is 1 again. So it's theta to the 8th over 8 factorial. Okay, I'm going to do 2 things at once here because we're almost out of time. I'm going to separate the ones that have eyes and that don't have eyes. So let's do the ones without eyes first. Sounds like I don't have eyes. Okay, so I've got 1 minus theta squared over 2 plus theta to the 4th over 4 factorial. I forgot the factorial over there. Minus theta to the 6th over 6 factorial plus theta to the 8th over 8 factorial. Plus, from the remaining terms that are odd powers of theta, I'm going to factor out the I. So I times theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial. And this goes on and on. Sorry, this should be done. Hey, look, those look super familiar. That looks exactly like cosine of theta. And that looks exactly like sine of theta. And it is really true, and this is what the formula says, that e to the I times theta is equal to cosine of theta plus I times sine of theta. It's a very, very famous formula, and there's a very famous equation that comes from it, where if you plug in, I think, pi for theta, so just note that e to the I times pi is equal to cosine of pi, which is -1. People write it as 0 minus 1, and sine of pi is 0. That's a very famous equation because it includes like the 5 most important numbers in math: 0, 1, e, I, and pi. But you don't really need to know that. What you need to know is this. And actually, you don't really need to know this, but I just want you to be aware of this because when if it comes up, and it probably will, it comes up when we talk about how to find the eigenvectors of these situations with complex eigenvalues, and it can just feel a little bit like, where is this all coming from? So now you'll know at least where this part's coming from. I know we're out of time, but just let me say one more thing. Taking it back to how our solution to a system of differential equations looks something like C1e to the lambda 1t times v1. The e to the lambda 1t is going to end up giving you this cosine plus sine part. And so what's going to happen is the real part of it is still going to make it either get bigger or smaller. Like if your eigenvalue is positive, your values get bigger. If your eigenvalue is negative, your values get smaller. But this other piece here, the imaginary part, what it's going to do is it's going to give us this oscillation, which is going to translate to being a spiral. Because as x and y get bigger, like either both get bigger or both get smaller, they're going to oscillate between getting bigger, and not quite as big. So that's what's going to happen. We'll talk more about that on Friday, on Valentine's Day.